Okay, so let's start off talking about the lab because that's somewhat relevant about the quiz. So here's the setup. So the first thing you did is that you mixed up straight KMnO4. Okay, so at this point you should be able to recognize this, that, oh, I've got potassium, monoatomic ion has a charge of 1 plus. Your MnO4 has a charge of 1 minus. So you have, and you got to get even just the terminology right. You got to know the difference between monoatomic, polyatomic. Polyatomic just means there's more than one atom. Not necessarily more than one type of atom, okay? But there's more than one atom. Most polyatomics have 2 different types. So you have potassium permanganate. So what happened is that potassium permanganate started off as that very, very, very dark purple powder, and you mixed it in with water, and it dissolved and turned into potassium ions and MnO4. Okay? It was just straight dissolved. That's all it did. So that had a certain molarity that you use. So what you want to do, and I want to make sure everybody starts off cool with this. So it says write the formula for this ion combined with oxygen. Okay? So what we're saying in here is that what you just mixed up is Mn7+. Okay? That's the oxidation state of manganese at that point. Okay? So in other words, here's what I want you to see is if you were to take that and bond that with oxygen, okay? The beauty of oxygen is that oxygen is monoatomic. Oxygen has 6 valence electrons. Oxygen except in one rare, very, very, very rare exception, and that's hydrogen peroxide. Oxygen always has a charge of 2 minus. Always, okay? Except if it's with peroxide, and don't worry about that for now. So you got manganese has a charge of 7 plus. Oxygen has a charge of 2 minus. Okay? So the easiest way to write this formula is just do that cross step. Take this 2, move it here, take that 7, move that there. And then you've got, the formula then is going to be Mn2O7. Okay, so when I ask you to write the formula for step 1, that's what I want, Mn2O7. Now, how can you always check that you have an ionic formula right? What do the oxidation numbers add up to?
0.
0. So here's how you can check that this is right. We're saying that manganese has a charge of 7 plus. So if I take 2 times 7, that gets me 14. I've got 7 oxygen. Each one of those is 2 minus. I take 7 times -2. I get -14. That all adds up to equal to 0. Boom, I'm done. Okay? Now, then on the next part it says write the name for this ion combined with oxygen. Oh, okay, since manganese has all these possible oxidation states, I'm going to write that as manganese, Roman numeral 7, oxide. Okay, that's all you have to do. Do not make this complicated. Okay, do not make this complicated. Okay. Now, the next one. So basically, what we did is we did this in steps. So what we did is that we allowed that manganese 7 plus to go from Mn7 plus, and then we dropped it down to Mn6 plus. Okay. So basically, what we did is that we allowed that manganese ion to only take in 1 electron. Okay, we didn't cascade it all the way down to 2 plus. We went in stages. Okay, so the first thing what we did is that we said, okay, we're going to take manganese, we're going to form it as 6 plus. So it's the same idea. Oh, Mn6 plus, and oxygen is 2 minus. Take that 2, move that here. Take that 6, move that here. You get Mn2O6. Now with this one, you actually want to reduce that down to its lowest form, okay? Just like 2/4 reduces down to 1/2, we want to reduce that down to its simplest whole number ratio, okay? So what's the simplest whole number ratio then? What's the simplest whole number ratio of Mn2O6?
MnO3.
Yeah, okay, thanks, Luke. Yeah, so this is gonna be MnO3, okay, because that's the simplest whole number ratio. Now, here's the deal. When you write, however, when you write the name of this, okay, when you write the name of this, you still need to write this as manganese 6 oxide. And if you have that as Mn2O6, it's horribly disciplined because of the fact that that's how you know that it's going to be 6. And that gets a little bit weird, but if you have it like that, that's fine. Okay? So do you see the pattern? Okay? So then we took manganese, we made it gain an electron, then we made it Mn5, then we made it Mn4, then Mn3, and Mn2. So that was the whole point. When you got done, you had that array of test tubes that had all these different oxidation states of manganese. Okay? Cool with that part. So when you get to and this is what you got to be able to do. So for example, on number 2, this is what you got to be able to do on the quiz. Oh, you got Na2SO3. So what's the name of this? Emma.
Sodium sulfide.
Sodium what?
Sulfide. Sulfate.
Nope. You had it right the first time. Sodium sulfite. So with sulfur gets a little bit confusing, then, because there's 3 different things you can have with sulfur. So let me point this out. If you have Na2S, that's sodium sulfide, okay? Because it's a monoatomic ion. That's sulfide. If you have sodium SO3, that is sulfite. And if you have Na2SO4, which is the most common of all of them, that's sodium sulfate. So ide, and ate, okay? You have 3 potential different endings on that. Okay, the same thing with nitrogen. You could have nitride, nitrite, and nitrate. Okay, so what do you know about ites versus ates? Which ones always have more oxygens?
A's.
Ates always have more oxygens than ites. Okay. So, any questions on the lab? Raman,
Yeah.
you act like you might have a question.
Can you explain 6 to me again?
Which question? 6.
On page 3.
Yep. Why is MnO4 a monoatomic or
I
polyatomic?
don't know those words very well.
Okay. Mono means 1.
Yeah.
Poly means more than 1.
Yeah, I know that, but like how do we?
So let me give you. Look. If you have S2 minus, okay, that's monoatomic. It's just 1 atom.
1. Yeah.
Okay. If you have SO4 2 minus, that's polyatomic because.
Oh, okay. I know now.
Does that make sense?
Yes, sir.
Okay. All right. Anything else? Emma, talk to me here.
Number 10.
Number 10? How many formula units? Okay. So here's the deal. So let's start with this. You have 0.10 grams of KMNO4, right? Let's actually back up the bus and let's talk about number 9. Okay, because if you got to have number 9 to do number 10. Okay. So I want to convert grams into moles. So remember, I'm going to put grams here, put moles up here if that's 1 mole. So how do you know what to put down there?
Cancel out the units.
Yep. So where are you going to look to find that number?
Periodic table.
Yeah. So you've got the potassium, the manganese, and you've got 4 oxygens. So what'd you get for the relative atomic mass of potassium per manganate?
158.03.
158.03. Everybody cool with that number? Anybody get anything different? We cool? Okay. So obviously you're not going to have very many moles of this stuff, right? This is going to be a very small number. Okay. So then, if you remember back to moles mole, you started up here in mass, right? And you went down here to moles. Now we need to go up here to the part store. So when you walk by this part of the mall, what number do you use? I'll give you a hint. It's a green fruit.
Oh, what?
Avocados, which is Avogadro's number, which is
6.02.
6.02 times 10 to the 23rd, right? So if you have 1 mole of anything, you have 6.02 times 10 to the 23rd. Okay? Now, because potassium permanganate is an ionic compound, instead of talking about molecules, we're talking about formula units. Okay?
So it's just a different name.
Yeah, so you're just going to take the number of moles that you got up there, whatever you got out of that conversion, and then go, oh, 1 mole is 6.02 times 10 to the 23rd. So basically, just take your answer from number 9 and multiply that by 6.02 times 10 to the 23rd. Okay, that's all you have to do. Do not make that complicated. Okay?
Don't make it complicated.
All right. Anything else? Going once? Ramen?
That was a joke. I was just joshing with
It's funny.
that. I know.
Not really. Okay. Twice sold. So get those handed in.
Yeah, I just don't know if that's really fun.
Okay, so let me explain how the quiz is going to go down. So initially up here, you put everything away, no periodic tables, no nothing. Okay? So on the first 7, what I did is I've given you the name, and then I want you to write the formula. And these are all the polyatomics. Okay? So I might say, what is NO2? So I might give you that. Say, hey, what's the name of it? Okay? Or I'm going to tell you, oh, here's nitrite, and write the formula. So those are the first 7. So when you get those done, call me over. I'm going to grade that top part. Okay? So here's going to be this top part. Those are going to be those first 7. Once I have graded that, then you can get out the periodic table with your choice. You can have the white one that has like the tables up at the top with the names. You can have whichever one that you want, okay? But what I would recommend is you use the one that has like the names up there at the top, just to, because that has everything on it. So, put everything away except for a pencil. Then when you get this part done, okay, you don't need a calculator. There's no, if you need a calculator for this, there's other issues, okay? So, have everything put away. Literally the only thing you need out is a pencil. Once you get the first ones done, then let me know and I will grade that part. And then once I get that graded, then you can begin the rest of it, where you either write the formula or you write the name. Now, I was nice, okay? When you name them, none of them are going to have Roman numerals, because I want to make sure everybody's comfortable with that before I assess you. So when you name the compounds, none of them will have Roman numerals. Now, when you write the formula, those will have Roman numerals. But when the naming part of it, you won't have any Roman numerals. Okay? So, here we go, kids. Okay, so let me kind of explain the number that's up there on the board and what that means. So, little background, back in 2018, I started the Native Solar Foundation. And here was my thought process, was that, yeah, I look at all the chemistry and all the research that's been done in terms of climate change and CO2 levels, and I'm just convinced that we can't keep going like we are. And I've never had any kids, and so the legacy that I wanted to leave was that solar project. So if you drove by, you see the solar panels out there, that was because of something that I started. And the reason I did it was because of the legacy that I learned from my dad, was that, you know, you were stewards of the earth and you're just passing through. And you leave the earth a better place than you found it. And so that's why I started it. And it's been more successful than I thought it was going to be honest. I really didn't have a plan when I started. It was like, if somebody said, hey, what's your timeline? How is it gonna work? And I would have said, I really don't know. I'm just kind of winging it. But it was just a gut feeling, because I knew I taught phenomenal kids, like I've taught uncles and moms of some of you that are in this room. And so I was taught here since 1993. And I just had this feeling that the people would come out and it would be a great thing. And so far we've raised raised close to $280,000 so far, almost $250,000. We've got this one up and running. Hopefully by the end of November we'll have solar panels on the roof of Prey Woodman. So ironically, I pull into the school every day and I can't see that solar array, but that's why I wanted them on Prey Woodman, so I can look over and I go, oh, there's the solar panels. Okay, cool. So one of the things that has kind of become a tradition, and Raman, you've spent some time looking at this. So this is one of the memorial panels that's down there in the front entrance of the school. And so, so this is my mom and dad, and there's some other ones that aren't here, like some uncles and aunts, some of my cousins, or some of my nephews and nieces, different graduating classes, and then different individual classes. So one of the things I want to explain is this one down here. This is done by Katie Riffle. Katie Riffle was the one that hung up and designed the stapler that's right up there. And so Katie was one of the first ones that donated to the campaign. She donated $1,000, and she gave me the Dr. Seuss book that says the Lorax, okay? And if you've never read that, I highly recommend that you do. It's a short little read. And one of the lines in that story is that unless people start carrying a whole lot, nothing will change, it won't. And so she didn't want her name on here. The only thing she wanted was the word unless. So this is Katie's. She didn't want her name, she just wanted that word unless. And so what's become the tradition, and like I said, this started technically in the fall of 2017, so that's why this is like the first set of classes. Like that's my first block honors, fall of 2017, third block, and then my AP physics class. So what that number represents, and this is collectively you all need to make this decision. You say, hey, do we want first block honors chemistry fall of 2022 up there on the memorial panel? So it'd be cool because you guys will be the only Chem 1 class to have a panel up there, okay? All the other panels from my other classes have been for my honors physics and for my AP classes. So if you collectively decide to do that, then you guys will be the first ever class that's a Chem 1 class up there. So when you guys come back for your 10, 20-year reunion, you look at that and go, hey, yeah, that was our class, we did that. So if you just wanted to buy the memorial panel, that donation is $740 because of the number of panels that are out there. That's how we came up with that number. So obviously I don't want you guys to raise $740. So what I did, and this is kind of how I do the formula, is that I say on average, If each of you donate $20, there's 15 of you, that's how I got the $300. So collectively, if you all donate $300, then we will have first block chemistry, okay, fall of 2022 up there on the next set of panels that are being built. So there's some options on how you can do that. So some kids like to buy the solar merch, okay? And so that's what I've got listed up there. So there's hooded sweatshirts. What we started last year, I don't know if you've ever seen this, the color changing ink. The chemistry on it was pretty cool. So it looks like a normal t-shirt and there's just an outline on the front of it, and which is the same thing as my tattoo. And if you're inside, it just looks like a white t-shirt with just like a black outline on it. But if you go out in the sun, then it changes colors to what you see up there on the display. And it is pretty cool. I mean, it changes instantly, but you have to be out in the sun to do it. So that's kind of a cool thing. So some people like that. That was actually a big hit last year. So that's an option. So there's hooded sweatshirts, there's t-shirts, there's long sleeve t-shirts, different things. So generally, I make about $10 if you buy one of those. So like if you buy like a hooded sweatshirt, oh, that will count $10 towards that total, okay? So that's an option. Like I'll have the children's book, Loopy, the Spirit of a Cow Dog. You know, if you want some of those for Christmas or whatever, you've got little nephews, nieces, whatever, or if you just want to buy someone donated to like the children's home or something like that, that'll give you about $10 per book, so that would count towards that. So that's an option as well. If you just want to say, hey, WordCamp, here's $10, that works too. So collectively as a class, you all need to decide, you know, is this something that we want to do? Okay, do we want to be the only Chem 1 class that has a panel up there? So literally, if you look at all of those, there are no Chem 1 classes up there. There's a lot of AP chemistry classes, AP physics, honors chem, or honors physics, but there's no Chem 1 classes up there. So if you want that, that's something that you all need to decide if that's something that you want. So anyway, I'd be honored if you did, you know, because that's one of the things that I look at when I look at that and I see, you know, like my mom and dad and, you know, different classes that I've taught and people that I've taught. And so it's become this journey has become much more spiritual than I thought it was going to be. Then especially now with the children's book and, you know, being able to donate the money from that. Because I wrote that book, you know, the year after my dad died. And so it's become very cool. It's become a cool legacy. So anyway, so that's something that you all need to decide if that's something that you want to do. So there's no pressure. If you don't want to say, hey, I don't want one person to do it. I don't want one person to donate $300, okay? I want this to be a class thing, okay? So that's, and you have until now, until December, the last day of school, to reach that point. It isn't like, oh, we have to have it by the end of the week. But if you do want to order any of the solar merch, I need that order by the end of the week. So that way I can get that placed, so I can get that back before Christmas. Okay, so if you're looking for a Christmas present, you can go to the parental units and go, hey, this is what I want for Christmas. Okay, so that's an option. All right. So here's what we have left. It looks like the big test over all of this stuff. Maybe Wednesday, Thursday, there really isn't that much left to do. We need to name, naming binary molecular compounds, naming some acids, and that's really about all we really have left. So there isn't all that much to go. Then we can get into the heart and soul of writing and balancing chemical equations. Okay, so on page 13 of the packet, let's talk about that. So this just gives you some examples. So here's what's different. When you name molecular compounds, you have to designate the numbers, and here's what's different. So let's say, for example, if you have sodium chloride, NaCl. If you tell me, hey, Burkamp, I need that bottle of sodium chloride, I know that the only way that you can write the formula for sodium chloride is NaCl. mainly because of the fact that the oxidation numbers have to add up to equal to 0. So sodium is 1 plus, chlorine is 1 minus. That adds up to equal to 0. That is the only way that these can exist, because they are forming ionic compounds, because the number of electrons lost has to equal the number of electrons gained. There is no possible other combination. Okay, I cannot have NaCl2. I cannot have Na2Cl4. Okay, can't exist. Mother Nature's lazy prima donna. Mother Nature goes, no, screw it, I'm not going to allow it to happen. I know it's only going to be NaCl. Now, when you get to compounds that share electrons, that have high electronegativity, and this is only going to be happening with your nonmetals, those elements in the top right-hand corner. So here's the classic example. So right now, you all are breathing out this molecule. It's a byproduct of your respiratory process happening on a cellular level, otherwise known as carbon dioxide. Okay? So you all are breathing this out right now. It's okay. Don't worry about it. Don't feel bad about it. Oh my God, I'm adding to global warming. It's okay. Okay? There are a whole bunch of other sources. Don't worry about it. Okay? Now, but what can cause poisoning, though, is this molecule, which is carbon monoxide. So this is carbon monoxide. So here's the problem. If it says to me, it says, hey, Mr. Burkamp, I need carbon oxide. Here's the problem. I don't know which one that she needs, because carbon and oxygen can combine together in different ways. So because, and this is the most important thing, the reason that there can be different combinations is because the electrons are being shared between the carbon and the oxygen. They aren't being transferred because both of them have such a high electronegativity that they basically don't have the ability to take electrons from the other one. So they go, hey, this is a tug of war. Neither one of us are going to win. We need to form a bond. Let's just share the electrons. Okay, so it's like a condo timeshare in Hawaii. Okay, you don't own it. You just kind of go there and you share it. You don't actually own it. You don't transfer that ownership. So, because, now listen to the vocabulary. Binary molecular compounds. Bi meaning two. So this only applies to two compounds. Okay, like nitrogen, oxygen, fluorine, and chlorine. Okay, because the fact that we're only going to be doing two of them, and they're going to share their electrons, we had to come up with a different way of naming them. So what we did, and this is what's on page 13, okay, and these prefixes are also listed on this flow chart that I gave you, because some people like a visual organization. So basically what this does is it kind of takes you through and says, okay, hey, how am I going to name this thing? So the first decision that you need to make is the first element a compound. Is the first compound a metal? Okay, so for example, if you have sodium chloride, yes, as soon as you see sodium, lithium, potassium, iron, copper, something like that, you know it's an ionic compound. Then, does it have more than one oxidation state? Oh, copper, iron, manganese. Oh, then I'm going to have to put Roman numerals on the end of it. Now, if it doesn't, and the one exception of this is ammonium, which contains NH4, that's the only ionic compound that starts with nonmetals, then you've got to use prefixes. So this is what is listed here. Okay. Now this list actually goes all the way through 10. That's rare that you get anything past about 5. Okay. But those are all listed here. So on page 13 of this, you need to fill out what these numeric values mean, okay, like 2 all the way through. So basically, and that's what I've got here. So di, tri, tetra, penta, hexa, and hepta. Okay, so that's going to form the basis. So this list is the same as this list. So, and I cannot emphasize this enough. This is why I gave you that flow chart. you are only going to do this, listen to me, you're only going to go through this process if you have two non-metals. Okay, that's it. I'm never going to expect you to do this with 3 non-metals, 4 non-metals. This will only exist with 2 non-metals. Okay, so here's what you've got. So over here, you've got all these different examples, okay, and how they're named. So for example, this one that I just built, okay, so the blues are nitrogen and the reds are oxygen. So if I said, hey, we need to name this thing. So right away, I know in this situation, I've got 2 nitrogens bounded to 3 oxygens, okay? So now I need to name this. Now here's what I can't do. I can't say, hey, Grace, what's the molecule that you built? And Grace just says, oh, Mr. Burkamp, that's nitrogen oxide. Okay? So here, that's why this is problematic. Nitrogen and oxygen, because of sharing their electrons, can combine in all sorts of different ways. And that's a 2-day long lecture in AP chemistry on what's called the hybridization of orbitals. Okay? And that's how we determine how they actually bond together. So for now, don't worry about that. Here's what I do know. If Grace says, hey, Mr. Burkamp, I built a molecule and it's nitrogen oxide, I'm going to say, Grace, that's amazing. Okay, it's cool. Happy for you. But I don't know what the combinations are because of the fact that they combine in different ratios. Okay, so that means I got to figure out how am I going to name this. So here's the deal. The beauty of it is you don't have to worry about oxidation states. You don't have to worry about things adding up to equal to 0. All you have to do is just name them. So I look at this and I got, oh, I've got 2 nitrogens. Okay, that's cool. So the prefix for 2 is, if you look on your chart, oh, that's di. So I got dinitrogen. So as soon as I see that, I know I have 2 nitrogens, okay? So the di, and here's what's going to be different, okay? And this is what you have to think through. The di indicates the number of particles, okay? Now, that's different if you have iron 3 oxide, okay? So if I have iron 3 oxide, if you have a Roman numeral, that indicates the oxidation state. But the prefix here as di indicates the number of particles because there's no oxidation state because we're not forming ions because we're not transferring electrons. Okay, so this is where it becomes like a logic problem. It's like, oh, I'm not transferring electrons, I'm not forming ions, I don't have to worry about oxidation states because I'm not actually losing or gaining electrons. I'm just sharing the electrons, okay? So I got dinitrogen. Then I look at this and I've got 3 oxygens. So I'm going to go dinitrogen, and then I'm going to put trioxide. So dinitrogen trioxide. As soon as I see that, then I know, oh, this is cool. I know exactly what this is. That's going to be O3. So here's what's different. Listen to me very carefully. Your prefixes, when you name these, don't indicate oxidation states. They don't indicate oxidation states because we're not forming ions, because we're just sharing electrons. Okay? And again, this will only happen when you have atoms that are in the top right-hand corner of the periodic table. Okay? This will never happen with metals. So whatever, I don't want to see this. So like if I gave you this, so this is going to be Fe3 plus, oxygen is 2 minus, that's going to be Fe2O3. You will never do this. Don't ever come in here and go, oh, that's diiron trioxide. Okay? No, bad, horrible, stop. You will never put a prefix in front of a metal. Okay, it's not going to happen, right? Don't, stop. You will only put these in front of 2 non-metals. The exception of that being NH4, which is ammonia. This is the only one, okay, that will start with non-metals that you don't use the prefixes on. So if you look like on this one, okay, so the blues are nitrogens, the yellows are sulfurs, okay? So I've got N2, S2. Now, if you just say, hey, Burkamp, that's nitrogen sulfide, that's cool. I don't know what the combination is. So I've got 2 of each. So the prefix for 2 is going to be di. So this is going to be dinitrogen, disulfide. Now, here's one thing that's still true. When you have the second element, that still ends in IDE. Okay? So just like sodium chloride is NaCl, and we change that ending to IDE, the same thing is going to be true here. This is going to be dinitrogen disulfide. So here's what I would recommend. This is just figuring out the pattern. Okay, literally, it's just figuring out the pattern. So what I would recommend is you just start with ones that you know, because then you can figure that out. It's like, oh, this is carbon monoxide. Okay, it's a poisonous gas. Don't breathe it in large quantities. Bad things are going to happen. Carbon monoxide forms what's called a terminal bond with the hemoglobin in your blood. Therefore, your body cannot get rid of the carbon dioxide, and what happens is your carbon dioxide builds up. You can't get it to your lungs to breathe it out, and you die of carbon monoxide poisoning. Oh, carbon monoxide, cool. CO2, that's still going to be carbon, and then that's going to be dioxide. Oh, okay, cool, right? Got that one. Now, pick another one. Like, let's say, for example, you have N2O3. Oh, that's dinitrogen trioxide. Okay? So here's the pattern. Literally, these 3 show you the pattern. Okay, hey, carbon monoxide. Mono means 1, dioxide's 2. Notice that I don't put a mono in front of the first one. Even though there's only 1 carbon, I don't call that monocarbon monoxide. Okay? So if there's nothing in front of the first element, you just assume that it's 1. Okay, it's just extra work. So if there's nothing there, you just assume that there's 1. Notice that you end those last ones with IDE. So if you can figure out this pattern, literally, just write this down. This forms the pattern of everything else. Oh, N2O3, di, boom, I have 3. Tri, I have 3. Or di is 2, tri is 3. I changed the ending to IDE. There you go. Okay, that's it. Now, there is kind of one subtle thing. And let's say that you have CF. Okay, there you go. So if I ask you to name this, you only have 1 carbon. Now, you only have 1 fluorine. So that's going to be carbon monofluoride. Now here's what's different. CO is carbon monoxide. So when you have a non-metal, that second one, and it starts with like oxygen, don't call that carbon monoxide. Okay? It just doesn't sound right. So if it's like something like fluorine, you keep the whole mono. It's monofluoride. But if it's starts with a vowel, you just leave that off. Then it's just mon and then the name of carbon monoxide. So that's why I said if you can figure out some simple examples, everything else just follows the pattern. Okay? So that's what I'd say, hey, just write down some simple ideas. So over here on this, down here on the bottom of page 13, basically it's got the rules that we just worked through. Okay? What I would recommend is if you're not sure about that, just look at the examples, right? That's the pattern. So over here on page 14, okay? So let's go through some of these, make sure everybody's cool with what I want. So your homework for tomorrow is to fill out page 14, okay? That's it. Just get through page 14. So let's say that you have CCl4. So CCl4 is one of my favorites, okay? It's on one of my favorite molecules. So here I've got carbon, and let me grab some. So let's say that you've got, these are fluorines. Okay? So this is CCl4. So notice I've got one carbon surrounded by 4 chlorines. So this is going to be carbon, and then what am I going to do, Luke? What's a prefix for 4?
Tetra.
Yeah, so this is going to be carbon tetrafluoride. It's an industrial solvent. It's fairly nasty. If someone ever offers you a drink of carbon tetrafluoride, don't take it. Okay? Bad things are going to happen. I'm just telling you, bad things are going to happen. So then where it gets a little bit tricky is that let's say that you've got SO. So, literally. Grace, how am I going to name so?
It would be sulfur
Fantastic.
mon. Would it use monoxide?
Yeah, it's just monoxide. Okay? I don't put that second O in there because that just kind of sounds redundant. So it's just sulfur monoxide. Just like CO is carbon monoxide, this would be sulfur monoxide. Okay, that's the only difference between the two of them. IBR5. So Emma, let's name this one. So I is what?
Iodine.
Yeah. So notice on the first one, I don't change the ending, okay? The first name that I write, I don't change the ending. The only thing I do with the first one is maybe put a prefix in front of it, okay? So that's just iodine. Now, I got 5 bromines. So what's the prefix for 5? Penta. So this would be iodine penta bromide. Go with that one. Okay? Notice that there's no oxidation states, there's no Roman numerals. You just use prefixes. Now, you get down to where you have to write the formulas. So you have dicarbon, hept oxide. So, Raman, what am I going to do with the dicarbon?
C2.
Fantastic. And then the hept oxide.
O7.
You sure?
What was it? Hepta?
You're fine.
Okay.
So C2O7. Why don't I have to worry about oxidation states adding up to equal to 0? Carter. Explain it in terms of electrons shared versus electrons transferred. Are the carbon and oxygen transferring electrons or just sharing electrons? Shared. Yeah, because they're just sharing electrons, I don't form ions. If I don't form ions, I don't have to worry about oxidation states. If I don't have oxidation states, I don't have to worry about those adding up to equal to 0. Okay? Got the idea? So, get through page 14 for tomorrow. Okay? If you want to just take an order form, if you want to show Ma, Pa, Kettle, kind of begin to think through that process. here are the order forms. There, that's what they all look like up there. So, there are those. I don't necessarily need the money by Friday, but I definitely need the order by Friday. We got it? We're good? Okay.